In the previous session, we talked about various ways to represent our input. In this session, we will present various ways to represent our output of data mining algorithms, or what we popularly call as knowledge. The topics that we will be covering are uh, how knowledge can be represented in the form of decision tables, decision trees. Then another way is to represent them in the form of rules, and we have two categorization of rules, that is classification and association rules. Then we will deal with some exceptional cases like involving exceptions and relations. Then we'll talk about numerical prediction, and in the end we'll be doing instance based representation as well as clustering. So let's begin with decision tables. So this is the simplest way to represent our output, and basically what we are doing, we are basically representing our output exactly the same way we represent our input. As you can see in the table below, we have our attributes, that is outlook, temperature, humidity and windy, as well as the class, that is play, in the same table. One thing which is important is the selection of attribute. Only attribute contributing to the result should be a part of a table. Otherwise, if you include attribute which do not contribute substantially to the results, then we'll end up using more time and resources to get our results. Another way of representing our knowledge is decision trees. Decision tree basically uses divide and conquer approach to give us the result in the form of a decision tree. Here you can see a decision tree. As you can notice, at each node we are testing an attribute for a particular condition. For example, as you can see here, we are checking the value of humidity, whether it's less than or equal to a specific value or it's greater than that value. And for the leaf of this tree we have the classification, and whatever instance reaches to a particular leaf, the classification which the leaf contains is the classification of that instance. So basically, again, what we just tell you, nodes in a decision tree involve testing a particular attribute. Leaf node give a classification that apply to all instances that reach that leaf, and the number of child emerging from a node depends on the type of attribute being tested in the node. For example, here we have a nominal attribute outlook, which can have three values, that is sunny, overcast or rainy, and since it has three values, therefore it can branch into three. And for numerical attribute, we can have various number of branches, but usually we have two branches, where one branch is less than and equal to, and the other one is greater than a specific numerical value. The next way of representation of knowledge is classification rule. They are a pretty common alternative to decision trees. A classification rule consists of two parts, the antecedent and the consequent. If you remember, a general classification rule is of the form: if some condition holds true, then we have some conclusion. So the condition which should hold true are called the antecedent, and the conclusion which we'll get if the antecedent holds true is called consequent. Moving ahead, now we will compare rules and trees. Uh, we'll talk about a problem called replicated subtree problem. Sometimes the transformation of rules into trees is impractical. Let's consider the following classification rule: if A and B, then X; if C and D, then X. These are pretty simple classification rule, but if you map them in the form of a decision tree, we get the following decision tree. Now the problem with this decision tree is that you can see some subnodes of the tree are replicated. For example, the D node, as you can see, it's marked gray over there, it's replicated twice in the same tree. So this type of a problem is called a replicated subtree problem. So basically we have two advantages of rules over tree. Rules are usually more compact than trees, as we just observed, and new rules can be added to the existing rules without disturbing the ones already there. Whereas if we need to make some modification in a tree, it may require complete reshaping of the tree. But having said that, trees do have some advantages over rules. Because of the redundancy present in the tree, any sort of ambiguity is avoided. and an instance might be encountered that the rule fails to classify, or it might classify it in two different classes, but this is usually not the case with trees. So these are the two advantages of trees over rules. Moving ahead to disjunctive normal form. A rule in disjunctive normal form basically follows closed world assumption. We have already talked about closed world assumption. Closed world assumption helps in avoiding ambiguities. As you remember, in the previous slide we talked about the problems with rules, and ambiguity was one of the problem. So a closed world assumption avoid that problem. And these rules, that is rules in disjunctive normal form, are written as logical expression, that is in the form of or and. uh, the next way of representation of knowledge is association rule. As we have already talked about, association rule can predict any attribute and not just the class. It can predict any number of attribute, and it can predict any combination of attributes. To select an association which apply to a large number of instances and have high accuracy, we use the following parameter to select the association rule. Now these parameters are important. Whenever we talk of algorithm for association rule, we basically specify these two parameters. These two parameters are the coverage, that is the number of instances for which our association rule predicts correctly. And the second thing is the accuracy, that is the number of instances it predicts correctly, or the coverage, in proportion to all the instances to which it is applied. So these two parameters are very crucial when we talk of association rules: coverage as well as accuracy. Now talking of exceptional rule, for classification rules, uh, we might encounter a case which is not properly classified by the classification rules which we have. In such cases, instead of manipulating our classification rule, we can just add an exception to that rule. As you can see in the example, we have used the keyword except to mention the exception. Now we can have an exception to an exception and so on. And using exceptions, we basically have the facility to scale up really well. Another thing with rules is rules with relation. Till now we have talked about propositional rule, where we are comparing an attribute to a constant. An example here, as you can see, we are comparing the attribute width, height, and with a constant 3.5 and 7.0 respectively. But we can have one more form of rules, that is relational rules, where we express relationship between attributes. So as you can see here in the below example, we can see we are comparing width and height, which are two attributes. So such type of rules are called relational rules. Standard relations which we can have in our relational rule are equality and inequality for nominal attributes, and comparison operator like less than and greater than with numeric attributes. Moving ahead, uh, we can do prediction for numerical attributes as well. We use decision tree for this. The right side of the rule or leaf of a tree, in case of a decision tree, would contain a numerical value. As you can remember in the decision tree which we saw in our previous slide, it contained a class value. For example, in the case of weather data, we have the value no or yes. In case of numerical value, we have an average of all the training set values to which the rule, in the case of rules, or leaf in the case of decision tree, applies. So we basically specify the average of all training set values for which the rule holds in the leaf. Prediction of numerical quantities is popularly called as regression, and therefore such kind of trees which are used for numerical prediction are called regression trees. Moving to our next type of learning, which is instance based learning. Till now what we have been doing is we are given a training set. From that training set we derive some type of rule, whether classification or association, etc. And from those rules we basically predict the class of unspecified instances. This is a new type of learning. What we'll be going to discuss now, which is called instance-based learning. In instance-based learning, we don't create rules, and we just store the instances directly. That is our training set. We just store our training set. All the real work is done during the classification of new instances. No pre-processing of training set, since we are not trying to get any kind of rules, so there is no pre-processing, and whatever work is done when we are trying to classify new instances. The new instances is compared with the existing instances, that is the training set, using a distance metric. Using the distance metric, the close existing instances is used to assign the class to a new one. So for example, you have 10 instances in your training set, and you get a new instance. So basically you will calculate the distance between the new instance and separately all the 10 instances taken one at a time using any distance metric, and the one having the least distance. So say for example, our unspecified, our new instance has a minimum distance with say instance number 5, so both of them will get the same class. So we'll use the class of instance number 5 and allot the same class to our new instance. This is how instance based learning works. Sometime more than one nearest neighbor is used. In the previous example, for example, we talked about only the fifth instance, which will assign the class to our new instance. But we can have a case where uh, we use more than one nearest neighbor, and the majority class of the closest k neighbor is assigned to a new instance. This technique is called k nearest neighbor method. And distance metric, we are talking about calculating distances between two instances, should be according to the data set. Most popular one is Euclidean distance, which is the most easiest one as well. In case of nominal attributes, see, in case of all distance metric, we need an integer or a real value which represents an attribute or an instance. In case of nominal attribute, distance metric has to be defined manually. For example, we can use any specification here. For an example, if two attributes are equal, then distance equals to 0, otherwise 1. So this is an example of how we can use distance metric with nominal attributes. Our next type of learning is clusters, which is our last type of knowledge representation we are going to talk about. When clusters rather than a classifier is learned, the output takes the form of a diagram which shows how the instances fall into cluster. So basically we divide the whole instance space into different clusters. We are going to show you some diagram which will help us imagine how clusters work. Here we are basically showing different output types of a cluster. In example A, you can see where we have divided our whole instance class into 3 sections. So each instance will belong to one and only one cluster. A different type of representation is shown in figure B, where basically we have used Venn diagrams, and we have divided the whole instance space using Venn diagram. Here the different thing is that an instance can fall in more than one cluster. As you can see with the case with K, J and G, they are basically lying in 2 or maybe more than 2 clusters as well. In the third form, what we are showing over here is we have 3 clusters, 1, 2 and 3, and we have instances A, B, C till H. What numerical values we are showing over here is the probability of an instance to fall in a cluster. So for example, A can fall into a cluster 1, and it has a probability of doing so of equal to 0.4. A falling into cluster 2 has a probability of 0.1, and for 3 it has a probability of 0.5. As you can very well infer that the sum of a row will be equal to 1, as any instance has to fall in one cluster or the other, and the sum cannot be greater than 1. These are the normal rules of probability. And the fourth type of clustering is over here. Here we are using a hierarchical scheme where we are dividing a cluster into subclusters, and we get kind of a hierarchical tree over here. So these are the four popular types of output representation in case of clusters. This ends our session on knowledge representation. Hope you enjoyed this session. Thank you.